In the previous video, we looked at inclined planes and how to do some calculations involving the ideal mechanical advantage. We will now take a look at screws and see how they are related to inclined planes. A screw is simply an inclined plane that is wrapped around a cylinder. An example of a screw might be an actual screw, a jack, or a drill bit. The distance the screw moves in one revolution is also the same distance between two successive threads on the screw. This distance is called the pitch of the screw. Typically, the pitch is very small, as you can see in the tiny red line on this screw indicating the pitch. Just like with inclined planes, we will be using the ideal mechanical advantage because there is a lot of friction with screws. The ideal mechanical advantage of a screw is equal to 2 times pi times the radius divided by the pitch. The radius will be the radius of the screwdriver, or the length of the handle of the jack screw, as seen in this picture. Since there are such large losses due to friction, we are going to discuss the efficiency of screws. Like previously mentioned, we use the ideal mechanical advantage instead of actual mechanical advantage or mechanical advantage due to friction. Because these simple machines are not 100% efficient, we can calculate the actual mechanical advantage as long as we know the ideal mechanical advantage and the efficiency. We can also calculate the ideal mechanical advantage if we know the efficiency and the actual mechanical advantage. Our base equation is actual mechanical advantage is equal to the efficiency multiplied by the ideal mechanical advantage. Our equation circle has AMA on top, efficiency, and IMA on the bottom. For completeness, our other equations are efficiency equals AMA divided by IMA, and IMA equals the AMA divided by the efficiency. In the next video, we will look at some calculations with screws.